Hello, everybody, and welcome to today's Jump Academic webinar. I'm Chuck London, and I'm on the academic team at Jump, and we'll be hosting today's event. Thanks again for joining. We will be taking questions throughout the event. If you have any questions, feel free to use the Q&A window as opposed to the chat window. It makes it easier for us to see and answer the questions. If for some reason we don't get to your question, or if you have a question after the event is over, we will be emailing out a recording of the webinar. Feel free to respond to that email with any questions that you may have. With that in mind, I'm going to pass it over to Ross Matusalem. Ross is an academic ambassador who will be going over the content. Ross, it's all yours.
Great. Thanks, Chuck. Thanks, everybody, for taking some time out of your day to talk about teaching advanced regression. Really, I think the title probably should add teaching advanced regression using JMP Student Edition, which, if you're not familiar, is a full-featured free version of JMP software for academic use, whether that's for teaching, learning, or research. And you can get it at jump.com/student. And I'm mentioning that today because some of the tools that we're going to see are exclusive to JMP Student Edition and our top commercial product, JMP Pro. Sometimes we get some commercial attendees at our academic webinars, which is great. If you're one of them, you're always welcome here. I just want you to know that if you're using standard or base JMP, some of the things we're seeing today, you actually won't have access to. But for our academic users, you all have access to JMP Student Edition at jump.com/student. So you will be able to do everything that we see today. I see somebody already commented in the Q&A, Ross sounds far away. That is unfortunate. Sounds like
Ross, I can confirm it does sound a little bit far away.
Yeah, normally this mic works. Let me try to switch microphones, everybody.
That's much better right there. I don't know.
I didn't do a darn thing, and it got better. So to be honest, I think sometimes the audio, noise cancellation is too smart by half. Let me just try to switch microphones and see what happens here. Just 1 second, everybody. All right, I'm on a different microphone. How does that sound, Chuck?
I can hear you much clearer. Thank you.
Beautiful. And to the anonymous attendee who flagged that at the beginning, thank you for flagging the audio issue at the beginning so we can get it addressed. Wonderful. Okay, everybody. So let's get back on track here. So today we're teaching advanced regression. This is really teaching regression techniques after students have established a foundation in basic least squares linear modeling. Now, if you would like to review the basics of using JMP to teach, least squares linear modeling, I want to point you to our on-demand webinar, Teaching Regression and ANOVA. As Chuck mentioned, we're going to email a link to the recording to all of you. And with that, you'll also be able to download this JMP journal file that I have on the left, pop it open, click this blue link, and it will take you to this Teaching Regression and ANOVA webinar. That covers all the basics of how to use FitModel, JMP's general purpose linear modeling tool for teaching, simple regression, multiple regression, also, factorial ANOVA. And we're not going to go back over those things today. But if you haven't seen that one, don't worry. You absolutely will be able to get plenty of knowledge and value out of today's webinar, but I do recommend that you go back and review the basics at some point. Okay, so with that, let's get in. By advanced regression today, we specifically mean stepwise regression, regularized regression, so things like lasso and elastic net models, and then generalized linear models. We're going to start with stepwise regression. And for that, and then also regularized regression, we're going to use the diabetes data set, which is bundled in JMP's sample data folder. You can always access JMP's sample data by going to Help and the sample index, which provides a browsable, searchable index of data tables. So I could just type diabetes in here to find it. Or we also have just a direct path to the sample data folder itself, which will pull up your file browser window where you have access to all of these data sets. But I've actually modified this one just a little bit for our purposes today. I've changed some of the variable names, and I've also added a couple additional variables. So you'll be able to get this version of the data set along with this journal when we send that link around. All right, all of that out of the way. Let's talk about this data set and why we might use stepwise regression on it. Then I'm going to walk you through the stepwise regression platform with plenty of tips and tricks for specifically for using it in a classroom setting. So our primary outcome of interest right now is this progression. So this is a quantitative measure of diabetes progression in 442 patients. And 6 months before the progression measure was taken, we have all of these different predictors like the person's age, their BMI, their blood pressure, and so forth, all the way down through their reported level of physical activity. And the idea is to build a linear model with some of these predictors that can best explain variability in that progression. So a model we can use to actually kind of forecast this patient's disease progression. The stepwise regression platform in JMP provides an interactive tool for stepping through the stepwise algorithm. And I'm going to walk through it in detail, but just to give you a quick preview of where we're going, it provides an interactive way to both step through the stepwise regression algorithm one step at a time, providing all the information about each step as we go along, way of running it all in one go to arrive at a final model, and when we do, easily running that model so that we get our standard least squares regression output directly from those selected model effects, and then do nice things, for example, like visualize our model with the prediction profiler, which we cover in more detail in that basic Regression ANOVA webinar that I showed before. So the interactivity of this stepwise regression platform, I think, makes it really great for teaching and helping students develop a conceptual understanding of how stepwise regression works. So let's actually back up and talk about this platform in some more detail. So stepwise regression is available in FitModel as one of FitModel's many personalities, and where a personality is just a modeling technique available. So I'm going to go to Analyze FitModel to get started. This is the FitModel launch dialog. We take our outcome or dependent variable, put it in the Y role. We'll take our predictors and put them into the model effects. For reasons that'll become clear in just a little bit, I'm going to start with the simple main effects model using only our continuous predictors. So I'll select those and click Add. And then critically under Personality, I'm going to select Stepwise right here. And this is how we get into JMP's Stepwise Regression tool. So that's all there is to launching it. So I'll click Run. And now we're already back to where I just started a moment ago, giving you that really quick 1-minute overview of the Stepwise platform. So let's actually walk through it now to show you how it works. I think the interface here should be relatively intuitive for folks who have even a basic familiarity with stepwise regression, which if you are teaching it, I hope that you do. We have a couple drop downs right here at the top for stopping rule and direction. So stopping rule, you can see we can base it on a couple information criterion. So the BIC or AIC corrected. You'll notice validation and k-fold R square grayed out right now. We will show in just a moment how to use cross-validation as a stopping rule, and then also a p-value threshold as well. So this is what's going to control when the stepwise algorithm stops stepping through adding variables to our regression model. The direction here, we can of course have forward stepwise, backward stepwise, or a mix of forward and backward, where terms can be entered into the model, but then also removed. So, as I showed at the outset, you can just click this Go button, and you can see as I hover over it, you're going to get a tooltip, and it says start stepping in the background until the stopping rule takes effect. And if I click Go, what's going to happen is it's going to iteratively add, because we had a forward direction, effects to our model until we hit an optimum value of this BIC criterion, and then it'll return the best model to us. And if you're familiar again with stepwise regression, all of this is probably just pretty simple, easy review for you. But now let's talk a little bit more about some tips for actually using this with students. So I'm going to reset things here. And this is something important to know, I think, when you're maybe working with this live with students in a classroom. And that's how to get back to a starting point, because you might run the algorithm multiple times. I'm first going to click Remove All to get all of our entered effects out of the model, those that were checked off in this estimates table down here. And then under our red triangle, and I saw at the outset on the poll, we have a couple folks who are new to JMP here. Red triangle menus live all over JMP inside all of its graphing and analysis tools, and they just provide more options for working with that tool. I'm going to go down to clear history, and you'll notice that table down at the bottom, step history, that summarizes all of the steps. We'll just go ahead and clear that. And so again, you can click Remove All, Clear History to get back to your starting point. Now then, let's talk about some things to know about these controls when using them with students. Well, first is that step button that you see to the right here allows you to, instead of running the algorithm in one go, step in the direction chosen, forward or backwards, just one step at a time. So I'll click step here, and you'll notice that BMI is the first effect added to the model. Here's the estimate, 10.2. Here's the sum squares accounted for by that, the F ratio, and then also the p-value associated with it in the model. And up above here, we have a statistical summary of the model itself. For example, we have the root mean squared error and the R squared and the AIC, and then crucially here, the BIC, which is what we're using as our stopping rule. That step has been added to the step history table. So we can see step 1, BMI was entered into the model. Its p-value is so small that it's being rounded to 0 here. The sequential sum of squares, so this is just the sum squared error that was accounted for by adding BMI to the model, and so forth down the line. And so I can click step again. The next step is going to enter LTG into the model. Here's the parameter estimate, 56. We see the sequential sum of squares, both reported up in the current estimates table and down here, and so forth. Note that you can also graph the step history by using the red triangle option, plot criterion history. And what that's going to do is actually show us the AIC and BIC values at each step. Where here, actually I should say, instead of step on the x-axis, it's the number of parameters in the model. So you can see right now we're at a 3-parameter model because we have an intercept and then the effect of BMI and the effect of LTG. Okay, so why am I showing you all this? Why does it matter? You know, most of the time we would just click go and get to a final model. I really think that using the iterative stepping through the model is a great way to help students develop their conceptual understanding of how stepwise regression works. For example, when we're doing forward regression, what is going to determine what gets added to the model next? Well, it's going to be the p-value in this case. So the term with the smallest p-value, which corresponds to, you know, the largest effect relative to the standard error of the estimate of that effect, that's what's going to get added next. So by stepping through iteratively, I could ask students, you know, what do you think is going to be added next and why? And they could, in fact, consult the p-value column right here to see what the p-value would be of any term were it to be entered next. And we can see that the smallest one is actually right here for blood pressure. So students can take their guess. I can click step and we can see, hey, were you right or wrong? Okay, so blood pressure has been entered. Another thing that you can do with this interactive interface is then note how parameter estimates and p-values for the existing terms change as you enter new effects into the model, which really this might be the first time where students are really confronted with that possibility, which can be counterintuitive, of course, right? I mean, how is the effect of BMI estimated differently depending on whether blood pressure is in the model? But down here under the step history table, there are these little radio buttons on the side. I can actually go back to before we entered blood pressure, and we can see the effect of BMI's 7.3 approximately. Here's our p-value, 1.2 times 10 to the negative 23rd. But now as we went forward and added blood pressure, the estimate for BMI and the p-value changed. So we can start to jump back and forth between steps and show how the estimates and all these other things actually change depending on what's been entered into the model. In this case, I mean, it's because blood pressure and BMI are correlated. So in fact, we can do that pretty easily with the quick fit y by x, which if you're not familiar with this tool, is just a tool for pairwise analyses of variables. So I can put BMI in my x, blood pressure in my y. And then in this case, I'm just going to ask for the summary statistics to get the correlation out. And here we go. It's about 0.4. We can also continue to step through the algorithm, noting the criterion history. And as we step through, you'll notice, especially for the BIC right here, it actually starts to go back up slightly. And so we can ask students as we step through, where should we have stopped right here, just based on what you're seeing in the graph? What's going to be the optimal stopping point if I were to hit that go button? Would it be the current model? Would it be one step before or another step before? So in fact, if I click go, then we can see that what we do is end up at the final model right here, where we have age, BMI, blood pressure, cholesterol, LDL, LTG, and glucose added into it. So my main point here, and aside from just giving you some just general ideas for how to use this step-by-step interactive interface, is just that really in doing so, you can help unlock some of the things in stepwise regression that I think might be otherwise maybe unintuitive or confusing for students. Now, a few things additionally to note about the interface here. And actually, let's go ahead. I'm just going to reset us again by clicking remove all and going to clear history. I mentioned before that in these stopping rules, we had max validation R square and k-fold R square. And when I've actually talked to folks who are teaching stepwise regression, a good number of them prefer to use some kind of cross-validation instead of these information criterion. Maybe it's more intuitive for students because they already understand R square at this point. If you're going to do that, you have a couple options, and I'm going to tell you which one I recommend, which is setting up a validation column in your data set. So you'll see in my data set right here, I have a column that splits my data into training and validation groups that then I can use where the stepwise algorithm will stop when performance on the training, or excuse me, the validation data levels off. But before that, I do want to show you under the red triangle, you have this option for k-fold cross-validation. So if I were to choose that, I could say maybe k is going to be 5. I should stop. I'm sorry, I'm making assumptions here. If you're not familiar with k-fold cross-validation here, the idea is that you split your data into k groups, in this case 5. You train your data on k-1 groups, so that would be 4 of the groups. And then you score the 5th group and then see what your R square is on that 5th group. And then you can do that repeatedly so that each of the 5 groups at some point serves as that holdout set or that validation set. And then you just stop when that procedure shows that the k-fold R square has leveled off. It stopped getting better. But anyways, I can go ahead and set 5, and I'll click OK here. Stopping rule has automatically updated to k-fold R square, and I can go ahead and click Go. And now you can even see down here in the step history, we've added k-fold R square, and that our top one observed was 0.4832, which if we actually look back up in the table, we can find it right here. So that was step number 5, the 6-parameter model. Now, why don't I recommend doing this with students? Well, because when you choose k-fold cross-validation up here, it's going to randomly assign rows into the K groups. Different students are going to get different random assignments, and then you start having students saying, my results aren't the same as yours, at least numerically, or maybe even, well, my model didn't have LTG and yours does, and I just don't understand, and we're just adding more confusion. So instead, what you can do, as I mentioned, is you can create validation columns. So this is for holdout validation that I've created here. You can also do k-fold validation, and that's using our make validation column utility. That way you know that there's no random assignment for each individual student. Everybody has the same rows in the data table assigned to the same groups. So let's say I wanted to create a, five-fold validation column. I would go to Analyze, Predictive Modeling, make validation column. Here under Selected Method, I can make what's just called a validation column, which is for holdout validation, or I could make, let's say, a k-fold validation column. It's going to want me to put my dependent variable in the y role, so I'll do that and click OK. Specify the number of folds. We'll go with 5 and then click Go. Now I have a k-fold cross-validation column right here. And when I go to fit model, let me just click recall and I'll get back to our setup before. I can take that 5-fold column. You'll notice I actually already had one hidden living in the data table, but that's all right. I can take that, put that in the validation role and click run. And now the Stepwise platform has defaulted to max k-fold r square. And now we're ready to run. And doing this ensures that every student has the same rows, again, assigned to the same groups to avoid that confusion of getting different results out. All right. Oh, let's see. A couple other things to note. One, if you're teaching backward selection, there's just something to know about the interface. So let me go back to just the bare start, which you'll notice I also, instead of clicking remove all and clearing history, I just went to redo and redo analysis this point. That's another way to get a clean slate. Let's say I'm teaching backward selection. And so I would imagine many of our students would do this, and we might even do this. So what I do is I go to direction, I click back, and then I just say, all right, let's start stepping through. And I don't know if you're hearing that sound come through the mic, but I'm getting a little error sound from my Mac. If I click go, in fact, same, and nothing's happening, and there would probably be some confusion. And that's because by default, we start with no terms entered into our model, which we can see right here. So what we should do first is click the Enter All button, and then we can start stepping through backwards and removing terms one at a time. Just a little gotcha. If you select backward, make sure to immediately select Enter All. I've found for myself, at least it's now, once you've done it enough, is basically muscle memory. As soon as I hit backwards, I just immediately click Enter All before doing anything else. Okay, but let's see. I'm going to remove all, go back to forward. Let's click Go. We'll get a final model. And now let's go ahead and run our model. You have two options here when you actually want to get to that standard least squares report once we've landed on this model that in this case contains 6 of our predictors here. I can click Run Model. Sorry, I did that with k-fold, and standard least squares didn't want to use the k-fold cross-validation column. That's fine. So we have gone straight into the least squares regression report here. And I find that that's generally the easiest way to do things here to minimize complexity for students. So that's the Run Model button here. You'll also notice a Make Model button. If I click Make Model, what happens? Well, it gets us back to the Fit Model Launch dialog with only our selected effects. You'll notice here's what standard least squares did not like my 5-fold column, so I could actually just remove that here. And then from there, I can click Run. Oh, I have the personality set to something different, so some of the outputs are different here, but the model's the same. Okay, so what's the difference and why would it matter? I'm going to show you one place where I've worked with several faculty where they have definitely found that they preferred this Make Model, which takes you back to that launch dialog, even though it adds an additional step for students. So let me show you why, and in doing so, talk about including categorical or higher order effects in your models. Okay, so let's go back. I'm going to go to Fit Model. We're going to predict progression. And now I'm going to take all 12 of our predictors, which include 3 categorical predictors. Sex is 2 level, family history is 2 level, physical activity is 3 level, low, medium, and high. And under our macros, I'm going to choose factorial to degree, where degree is set to 2, and this gives me a second order factorial model. So all the main effects and all the two-way interactions. Pretty, perhaps more realistic scenario for stepwise regression, where you have many possible model effects to select. Under personality, I'll go to stepwise and click run. All right, so now we have this big table under current estimates of all the possible effects. First thing to note here is how categorical effects are being constructed. All right, so we can see the main effect of sex right here, and it says sex, female minus male. This is telling me that this is an indicator variable. Male is the baseline, so the intercept would be a male. And then this parameter will estimate the deviation from the males for the females. Family history, same thing. Yes is the baseline, and so this parameter estimate will represent the difference between the yes and no family history. Where things get interesting is right here. Let's look at physical activity that had 3 levels. You'll notice that they're not indicator variables that you might be expecting. We have, for one of them, the difference between high and then grouping together the medium and low. And then we also have just the difference between medium and low. So basically taking this group and splitting them apart. The terms for categorical effects are constructed hierarchically in JMP's stepwise platform. What that means is basically you just create an indicator variable that groups levels together such that the 2 resulting groups, so one group here is just the high people, the other group is the medium and low, have maximally different means, or that is the, I should say more precisely, it maximizes the sum squares between. So that is if you're going to enter only one variable or one term for physical activity, you want to enter the one that explains the most variability. And this is how it does that. It determines ahead of time what the hierarchical construction should be and then places those variables in. Now that's a bit to absorb in just a moment, which is why in our journal right here, I provided links to the documentation for how these are constructed. So they're living right here for you to read up more on that. Now, another thing you're going to notice that's different here when I have categorical or higher order terms is you have this rules menu that wasn't here before. And so the rules menu allows you to specify how categorical and higher order terms are handled. So specifically when there's either some issue with respect to heredity, that is, you have an interaction term, should you force the main effects into the model before you put an interaction term in? And then again, with these categorical terms, should you be allowed to enter just one of the physical activity terms, or should you be forced to enter them both? You'll notice I have my rules defaulting to whole effects respecting heredity, where if we hover over whole effects, for example, you can see it only enters the whole effect rather than one parameter at a time for categorical variables with more than 2 levels. That means that if you're going to enter physical activity, you're going to enter both of those terms. You can't just enter one. Whole effects respecting heredity includes that, but then also says if you're going to include an interaction term, you have to include its main effects as well. Contrast that with, say, no rules. So let's go ahead and click go when there are just no rules. So anything is allowed to be entered on a given step. And let's take a look. Well, we've entered only one of the physical activity variables. We've also entered the age glucose by interaction, but we actually don't have an effective age, main effect, I should say, or one of glucose. So these rules become pretty important if you decide to teach stepwise with interaction terms or with 3+ level categorical terms. They really become pretty critical. I've included a link to the documentation here so that you can check what all of these different rules are. You may notice again, when you hover over them, you do get a tooltip explaining the basics of it. I personally find whole effects respecting heredity to be nice because you are ensuring that if you have a categorical variable entered into the model, all of its associated terms will be there. And if you have interactions, all the associated main effects will be there. So a fair bit of detail, but it's important to understand how categorical and higher order effects are handled by JMP's stepwise algorithm if you intend to teach stepwise with those additional complexities here. Now, finally, I did say when we got into this, I wanted to tell you then why I know a fair bit of people who prefer this make model button when they're using this. Let's say that physical activity got entered into the model and I click run model. Well, now you're going to see that these indicator variables that use this hierarchical coding have been entered. And this is not a typical way that students are going to be thinking about how categorical terms are represented in regression models. So here's what you can do instead. You can click make model. These categorical terms, these hierarchical terms that have been created are in italics here. And I can just remove them and instead just add physical activity back in. And now it will be coded how JMP normally does it with effects coding here. And so if we get down to our parameter estimates table, we see something that looks a little bit more familiar to students. All right. So quick review, stepwise regression in JMP. It's a personality in fit model. I highly recommend using the interactive stepping along with the ability to, here, if we remove all, just get a few going, the ability to revisit any individual steps in the process. Don't forget about the criterion history plot if you want to be able to actually plot the results. One thing I didn't mention, also, if you want to be able to plot any of the step history in a way that's not represented by that step history graph, if I pull that back up, you can always right-click inside a JMP table, go to Make into Data Table to pull out that information and then be able to feed this into Graph Builder or something else. For the sake of time, I won't show how I might do that. Then please consult the documentation links that I provided here about handling categorical or higher order effects. I think it's important to get familiar with those before you get this in front of your students. And then finally, I do want to point out, in the tool that we're going to next, which at JMP we call GenReg, it stands for Generalized Regression, there's also stepwise regression there as well. So I'm just going to give you a quick preview of GenReg. Let's say, here, I'll just add our 12 main effects here. Instead of going to stepwise, we go one more step down. In JMP, the generalized regression personality offers a lot of different fitting methods or estimation methods, a lot of different response distributions, all in one place. If I launch it, well, first you'll notice you'll get a standard least squares fit out. You'll notice we have forward selection, backward selection. We even have some additional things like best subset, which allows you to fit every possible model up to a certain number of terms and then select the best one. Careful with that one because you might end up at, incidentally trying to fit millions of models. Prune forward selection. The point here is that you can do stepwise in GenReg, but it has a more complex interface where if all you're focusing on is stepwise regression, I recommend just using the stepwise platform that I've shown already. You don't want students necessarily having to think about choosing response distributions if all you're doing is teaching stepwise. You don't want them going, oh, well, what's the Danzig selector? What's lasso? What's SVEM forward selection, which you're probably not teaching in a basic stepwise class. So all this to say is you can do it here in this tool we're about to take a closer look at, but I recommend, again, sticking with the stepwise personality instead. Okay. So we're going to talk about regularized regression next, but
Ross,
I'm going to take a swig and see if there are some questions.
Oh, perfect. Sorry, I didn't mean to step over you. There were a couple of questions in there.
All right. I got them up here, Chuck. I'll see what we got here.
There's a couple in the chat too once you get done.
Yeah, I see that. Okay, so somebody asked, will I discuss all subsets regression? I mentioned it briefly. We can take another quick look. I'm just, without trying to actually do it because it can take a little while. Let's say that we're back in our stepwise. I click run. So let's see. I think that's red triangle here. That's right. So in GenReg, it's called best subsets. You might also hear it referred to, and it is referred to here as all possible models. All possible models, what it's going to do, as I said, is fit all the possible models of all different combinations of predictors, or I should say terms that we entered here, and then return the best fitting one to you. Now here, when you launch this, it's going to say maximum number of terms in a model, and this would be 8 by default here, but I can change this. So that means anywhere from a 2-term model, because a 1-term model is just the intercept. So anywhere from a 2-term model to an 8-term model. Fit all of those possible models. And then return the 56 best performing ones. Now, if you try to do that, that's a lot of models to fit. And once you have even more possible terms in here, this number can get very large, and the number of models that can be fit can get very large. I'm going to drop it down to 3 and just click OK. And now we can see what happened here is that we fit just the BMI model, just the LTG model, just the blood pressure model. Coming up next, we did BMI and LTG, BMI and blood pressure, and all the way down until we have every possible model with 3 effects. We have the full history right here, and then we can select the best model from this group. So that's best subsets. I just highly recommend testing it out however you want to do it first if you're going to do it live, because again, and JMP will warn you, I should say, if it's about to fit millions and millions of models, it'll basically say, are you sure you want to do that? And if you're at least live in the classroom, the answer to that question is probably no. All right, we do have more questions. Thank you so much for engaging with me here. For the sake of time, we are going to move on. I see we're already 40 minutes deep. We will be sending that email following up with the link to the recording. You are encouraged to ask any questions that you have there, and we will make sure to respond to them. But with that, let's get to regularized regression here. We very briefly saw the GenReg, or generalized regression personality, in JMP, and this is where you're going to find regularized regression techniques. Now again, these teaching certain topics with JMP webinars assume that you already know the techniques themselves. This is more of a train the trainer kind of model. So I'm not going to go deep on what regularized regression is, but I will say, if you're not really familiar with it, the basic idea is to introduce a little bias to your parameter estimates, that is, bias them back towards 0 to try to avoid overfitting, right? You're kind of constraining your model so that it can't easily fit to the noise in your data. So here I have an example of a regularized regression model, in particular a lasso model in JMP's GenReg platform. So this is the same data set, so we're predicting disease progression based on a certain number of factors, and you can see that using our lasso model, we have zeroed out the effects of age, LDL, and TCH. We have the remaining parameter estimates right here. And what we're going to spend a few minutes exploring is this interactive solution path. So you'll notice that as I change our point in the solution path, so that is identifying the best lasso model here, all of our statistics update automatically. And much like the interactivity in the Stepwise platform, I think this interactivity affords a lot of great opportunities for helping students establish a conceptual understanding of what's going on. So let's actually build this model and then walk through this stuff in more detail here. So we're going to start again at fit model. If you're building a linear model in JMP, this is where you start. Again, our y variable is progression. I'm just going to put our 12 predictors in as main effects for our purposes here. And now I'm going to choose generalized regression. You'll note, and we'll talk about it in a moment, we have a distribution menu that pops up. We'll just leave it at normal and click run. By default, as I briefly mentioned, GenReg will just fit a standard least squares model to the data, which we can find down here. Now, you may choose to leave that up as a point of comparison when teaching regularized regression. I'm going to, for simplicity's sake here, go to the red triangle there, and you'll notice you can remove this fit. The thing in generalized regression is that you can fit and compare multiple models within one window, but you can remove any of them if you want by just clicking remove fit. Okay, now you'll notice I did not specify that I wanted a lasso model in the fit model launch, but I have that option to do it here. You can also see the other common regularized regression techniques that you might teach, ridge and elastic net living right there. So the estimation method is specified after launching the platform. And I just had this point of confusion a couple times with folks when they're inside fit model and they're saying, well, where is, when I go to generalized regression, where is the option to say I want a lasso model or I want a ridge model? You just click run once you get that set up, and then you'll find it under estimation method right here. So let's go ahead and click go, and that's going to fit our lasso regression model, and here it is. Now, if you have familiarity with these techniques, you know that the critical parameter here is known as lambda, and this is the regularization parameter. That is, it puts a penalty on the parameter estimates, tries to keep them from getting too big, or as I said before, helps bias them back towards zero. And you're going to find that lambda value reported under the measure table under model summary. And I just want to point that out because there are a lot of outputs right here. And this is, if you're teaching this, undoubtedly, this is going to be a primary focus for you. You're going to find it living right at the bottom, which, as I showed before, you can drag the solution path line around and note that the lambda is actually changing. So I'm looking at bigger penalties that is more biased towards zero for our parameter estimates. It's actually kind of nice that the lambda lives right there, I think, for teaching purposes, because as you show changing the model at different lambda values, that critical value is actually just right above the graph. Now, you'll notice I'm going to click reset solution. JMP settled on a lambda of 15.4. Well, how did it do that? GenReg automatically tunes or optimizes your lambda with a grid search. So that is, it just tries and fits a bunch of models at different lambda values and then returns the best one according to whatever your validation method was. In this case, again, like we were with Stepwise, it was the AIC. And you can actually see that graph of AIC at different lambda values that were tested right down here. And you can see that we find the lowest AIC right there. Now, this is done via a grid search that you have control over. So under advanced controls, we have a default of 150. So that's 150 different lambda values that were tried here. And we can specify how the grid is scaled. So we have 3 different options here. I'm not going to get into the details just for the sake of time. Please do pull up this journal and go to the advanced controls documentation right here, which is going to tell you about lambda, or the tuning parameter, how it's actually handled, along with these other advanced controls. And I recommend looking at statistical details for advanced controls, because here you're going to find some handy graphs about that grid scale. So you can see a linear grid scale. They're equal intervals between all the lambda values that are tried. Whereas a log scale, and I should note, lower lambda values are over here in this graph. So there's no regularization over here, really strict regularization over here. You'll notice when it's really strict, it's going in these big intervals of lambda. And then as it gets more relaxed, it starts testing very small intervals. The square root, which is the default, is somewhere between the two. That may or may not be too much detail for your students. I'm not sure if you're going to go that deep on how lambda is optimized, but if you are, these are important things to know. Otherwise, heck, leave that collapsed, tell students not to worry about it. Okay, now let's talk about exploring that solution path a little bit more here. So we have this graph, and it might take a moment for students to wrap their heads around what it is. But let me start over here. I've dragged this all the way to the right. This is the model that was fit with a lambda penalty of 0. This is our least squares regression. You can see all of the parameter estimates and so forth. And in fact, let me go ahead and pull up our prediction profiler. And you can see the visualization of all of our model effects right here. As I click and drag to the left, I'm starting to introduce some regularization. Here's lambda of 0.04, 0.17. You'll notice the parameter estimates table automatically updating. You can see how those parameter estimates are starting to shrink towards 0. Well, not quite all of them for some reasons we won't get into right now, but in general. In fact, once we start getting over here, you're going to notice that. Now, here's something that I find to help boost intuition, especially, sometimes I have to show, industry practitioners or academic researchers how to use these things to try to build an intuition for what's really happening. Let's take a look at a parameter of interest. Each one of these blue traces represents one. So I can click on one, for example, and even hover, and it says, this is the parameter estimate for LTG, and it was really big over here, and as we have lambda increasing, it gets smaller and smaller. Or here's the parameter estimate for, I think this is blood pressure, if I can get the hover label up. That's all right. Actually, it's BMI. Every selection I make on a parameter here will actually select it in the parameter estimates table. So let's look at the parameter estimate for BMI right here. We can, of course, here, I'll open that one more time, and let's close our model summary so we can kind of get off the bottom here. I can show how as I increase lambda, that BMI parameter is shrinking towards 0 and starts picking up quite heavily right here for really strict lambdas. But sometimes looking at a table of numbers isn't that helpful. Well, what about actually just looking at the prediction profiler? So here's the effect of BMI. We can see the slope of the line depicted right here. Well, what happens as lambda increases? You can actually see, oh, yeah, as we start getting pretty strict regularization, that's flattening out towards 0 until we get just two variables in the model, BMI and LTG, these two traces right here, and they're both near 0. So this interactive solution path will really help, I think, students establish a conceptual understanding for, again, as lambda changes, we'll bring that back up so it's just living right there, what's actually happening in the model and what that's doing to the parameter estimates and the fact that some variables are actually exiting the model, they're being zeroed out. Now, I should mention as well, if you want the actual numbers behind all of this, so a summary of the solution path itself, go ahead and under the red triangle regression reports, you can pull up the solution path summary right here. Now, I should mention briefly, we've seen it in a couple graphs when we're plotting the AIC or BIC, you're going to get green and yellow ranges. Anything in the green range is within 4 points of the lowest value observed. Anything within the yellow is outside of 4 points, but is within 10 points. So you'll see it in this table. You'll also see it right here. And when, oftentimes folks say that within 4 points is a roughly equivalent model, it just means anything inside this green range might be, we'll call an equivalent model. In fact, I can find a model over here, not quite as regularized. So we have a smaller lambda value of only about 2, but it's nearly at the same AIC value as the model over here. And if I click Reset Solution, it will just get back to the chosen model. And then final thing to note here, the graph's parameter estimates, so right here, these are scaled. So you'll notice, if we're looking at this parameter estimate for, as we see selected here, BMI, it's showing at 500 when the real parameter estimate is 5. So this is the magnitude of the centered and scaled parameter estimates, and these are the individual scaled parameter estimates up here. And if you want to get the direct correspondence for students under regression reports, you're going to find parameter estimates for centered and scaled predictors, and you'll have that table instead. And now you see a direct correspondence, 513 for BMI, which corresponds to the height of the blue line right there. All right, I see we're starting to run out of time. I told myself at the beginning that I would actually be able to do this, but again, thank you for all the questions. I see we have some more even coming in as we go. Again, I will answer those in email for those that we can't get to now. Let's see if there are things that I might want to just call out briefly here. Note that I've been using the AIC for the validation method here. That is for tuning that lambda parameter, but you can do k-fold and hold back or even leave one out cross-validation if you want. Same thing applies as with Stepwise. If you're going to do that, I highly recommend hard coding that in the data table using, again, analyze, predictive modeling, and make validation column. And then finally, and this topic I know for some is controversial, but you might be teaching it, and that is once you have run your model, you now have zeroed out, in this case, 3 of our predictors you might want to run a standard least squares model on those predictors, or do some refitting post variable selection. There's an easy way to do that. Under the red triangle next to your model, excuse me, I went to the very top one. Under the red triangle next to your model, go ahead and go to relaunch active set. And there, you can do something like a relaunch with only the active effects. And then maybe there even just go back to standard least squares and click run. And now I have a standard least squares with only those non-zero, or I should say with only those selected model effects. So a nice easy path so you don't have to fill out that dialog manually while consulting that parameter estimate table. All right, we have just a little bit about generalized linear models. Before we do that, I will just point out briefly, because I don't know that we'll have time at the very end, do consult in the journal, the teaching resources section right here. I have links to some of our learning library quick guides. So these are, 2 to 4 minute long videos on how to use JMP. And so there's a link to the correlation and regression guides right here. We also offer case studies. So these are data sets presenting real world problems and documentation with a multi-step solution path and JMP instructions. Click here to review those specifically for regression and linear modeling. And then also our online statistics course does have a component specifically on regularized regression. And you can click on these links to access that course and also request the instructor materials if you like. But now I'm going to talk briefly about using GenReg for teaching generalized linear models here. I'm going to pop open a new data set. This is another one bundled in JMP. It's the fishing data set, where we've surveyed 250 people after a visit to a state park with a large lake stocked with fish. And we asked them, how many fish did you catch? Did you use live bait or not? How many fishing poles was your group using? How many people were in your group? How many of those were children? And were you camping or not? And we're using this to try to build a model to be able to predict for any given people how many fish they might catch in order to then just better understand how we should stock the pond, how we should create fishing restrictions, and so forth. So crucially, the number of fish caught, that's not going to be normally distributed. That can only take integer values. They're only positive. If you're familiar with generalized linear models, you probably immediately identify this as a Poisson model. Now, I have some additional notes in here that you can review on your own time. Again, I'm terribly sorry for not having time to get to them. First thing you might do with students in a classroom is demonstrate non-normality. So I've included instructions here where you could fit a standard least squares regression model and then actually pull up residual plots or put residuals into JMP's distribution platform to demonstrate the non-normality. But the big thing when teaching generalized linear models is talking about the different distributions and then also the distinction between the linear predictor and the link function and how both are necessary to actually be able to build a linear model that can predict this non-normal response variable. So let's just talk very briefly about that. One thing I showed at the outset with GenReg, and let's say I'm going to do fish caught is my Y. I'm going to add our 5 just main effects for our model here and then go down to GenReg. You have a lot of different distributions. You may recall that when we were inside the platform, you have a distribution menu as well. And that's again because you can fit multiple models inside GenReg once you're in the window. I recommend choosing the distribution here, though. So I'm going to go ahead and choose a Poisson model. Click Run. And now I have a Poisson model with maximum likelihood estimation. I have my parameter estimates here. I can pull up my profiler right here. And this profiler, thankfully, it's not just profiling on the linear predictor itself, but it's using the link function so that the response variable is, in fact, the expected, in this case, number of fish being caught, or the expected rate here. Note, though, that under model launch, our default is Poisson because that's what we chose at the outset. It would be normal had we chosen something else, but the estimation method now defaults to lasso. So if I were to go to fit model and then just leave this as normal and click run and then say, oh, well, I really wanted to do a Poisson model. Well, you also need to remember in that case to change the estimation method to maximum likelihood in the context of just teaching your standard, ML estimation for these generalized linear models. And that's a potential failure point, right? Students forgetting to go set maximum likelihood or even just asking, why the heck do I have to do that? So that's why I recommend actually choosing that response distribution up front. Now, just a couple quick things to note. Again, if you're teaching this, you're probably focusing on the link function to some degree. That's going to be reported right here under model summary. So here we have a log link function. And another thing to note is when talking about the distinction here, or basically the distinction between what the linear predictor spits out and how you need the link function to link it to the response distribution, you have the option under the red triangle, if you go to save columns, to save either the prediction formula, but also one that I found, most folks don't even know is there, is you can save the linear predictor itself to your data table. So if I go back, I have a new formula column in my data table that is just the linear predictor. And I can use this to help try to teach students, well, this obviously isn't predicting, the number of fish caught. You can't catch negative 1.63 fish, but the linear predictor can go negative. So what we're predicting is the log of the expected number of fish caught. And so maybe what I would do is right click and go to new formula column and say just exponentiate that. And now we have the number of fish caught. In fact, we could really quickly, if you wanted to, enter some of these factor values into the profiler and find out that, in fact, yes, the predicted exponentiated linear predictor is 3.2 fish approximately. Now I see we're running up against time, so I'm going to leave us with just one more thing. You are going to notice, and this is a question I've gotten a good number of times, that JMP has both generalized regression, which again has all of these different response distributions, but it also has generalized linear model down here. And you can choose a more limited set of distributions. So folks ask, well, why GLM versus GenReg, and why would I choose one over the other? Well, first part of the answer is generalized linear model brings GLMs to base JMP. So if you have base JMP, you don't have GenReg, but you will have generalized linear model, allowing you to fit some of the most basic ones, like binomial distribution for logistic regression, or Poisson, or exponential. But it also has some nice properties. So you can set the link function yourself. If you want to teach probit regression, this is where you're going to want to do it. And you also have these options for overdispersion tests and Firth estimates, which I've encountered a couple folks who are, in fact, teaching those directly, in which case generalized linear model is the way to go. Now, I've included all of this information in the notes and can answer more questions on it, but I know this is a point of potential confusion for a lot of folks. Why are there two? What are the differences? I personally prefer GenReg because it's a more general purpose model. You can actually combine non-normal response distributions with other than maximum likelihood estimation techniques. So really, if you're teaching, full-blown advanced regression and tying it all together, that's the one tool to use. But we're at the top of the hour. I see we have a number of questions. I'm going to stick around for as long as people are willing to try to answer those questions. But thank you very much for your time and attention today. And Chuck, thank you for hosting. So with that, Chuck, let's try to handle some of these questions here.
Perfect, Ross. Thank you so much for everything. I can try to help you navigate.
Yeah, I see a fair bit have popped up in the chat. We do have some in the Q&A as well. I see somebody asked, and this was back at 12:26 p.m. Eastern US time, so that would have been during Stepwise. Are there concerns about overfitting with Stepwise? Stepwise is designed to try to avoid overfitting. So if I just go back, whoops, I'm on the wrong data set here. So I'm going to go to fit model and just bring us back. The stopping rules, especially AIC, BIC, or validation R square, are meant to avoid overfitting. So the idea is somewhat clear. You know, let's actually, I'm just going to pull up k-fold cross-validation here again. We'll go 5-fold, and I'll click go. So we've chosen all but 2 of our effects here. But the idea is that we're trying to avoid overfitting by withholding some data and then only adding variables or model effects if those actually improve our ability to explain variance in the data that was not used in the model. That ability is summarized right here by our k-fold r square. And you can see that it keeps climbing to a particular point, 5.5059, before starting to fall again. And that falling is actually indicative of overfitting. In fact, let me actually relaunch the analysis. But what we're going to do is get back to our second order factorial, because here is where we can really see the effects. So let's do k-fold, and I'll click go. We can notice right here that our k-fold r square starts to climb and climb. The model's getting better at predicting things. And then once we hit the peak, it starts to fall back off more substantially. In fact, I'm going to go to make into data table and just make a quick graph of this so we can see. So let's take a look at the step in the stepwise procedure against that r square k-fold. And I'm just going to remove our smoother and go like this. Oh, and this is actually our best model, which is always appended to the end of that table. So let's go ahead and get that out of here. So this is a graph that demonstrates the possibility of overfitting. So higher values are better. So as we step through the algorithm and we start adding terms to the model gets better for a bit. It starts really kind of plateauing, and then it starts falling back off. This right here is overfitting, which is why it returns the best model, which was with that k-fold r square of 0.5176, which is actually all the way back here at step 13. All of these were determined to essentially be overfitting, and so these terms, showing what was being added at that time, were not added for that reason. So that was a long answer, but the short answer is, done properly, stepwise regression is built to avoid overfitting. Oh, here we go. Do you interpret the biased estimates from regularized regression and compare to unbiased estimates from least squares? Using biased estimates, are you primarily interested in prediction of Y or explaining relationships between predictors and outcomes? Okay, so this, in my experience, is somewhat of a hotly debated topic. I've actually, just out of curiosity, not even that long ago, went on to some discussion boards. You know, there's a Reddit statistics board there, you know, a Stack Exchange, all these places, and people sometimes get heated with each other around this exact issue. But let me back up for folks who might not know the details here. So with something like a lasso model that we talked about, and I can pull it back up for expository purposes. Let me not save that. We'll just get rid of all this. Okay. So again, regularized regression, we're biasing our parameter estimates towards 0. In a lasso model, we might literally make some of them 0, like age and LDL and TCH right here. These other estimates, they are biased towards 0 as well. So for example, right here, we have the effective LTG at 46. The standard least squares solution with all of them in, it would actually be 71. So what can you trust, right? Or is the effective LTG 76 or excuse me, was it I'm already losing it. Yes, 46, excuse me, or is it 71? That might matter. Some folks say, well, what you should do is use lasso for variable selection and then do that refitting. So again, in JMP, you'd go to relaunch active set, relaunch with active effects. Maybe just go to least squares, even though you could do that in GenReg. Click run, and here you go. And now you get your LTG estimate. Actually, neither of those. It's 48 with just these variables. Some argue that for inference, that is, what's the real effect of LTG, that this is what you should do. Others point out the fact that least squares estimates themselves aren't necessarily unbiased. They're unbiased if the model's correct. That is, if you have all of the right terms in the model. If you exclude certain terms that have an effect and that are also correlated with our predictors, then these estimates are in fact still biased. I mean, you couldn't know that. Maybe you've never actually measured the one thing that's essentially a confounder. So some folks say, well, heck, you very well might be getting biased estimates either way, so pick your poison. It's probably some validity to that. But still, it could be the case that knowing that you've introduced bias towards zero by using a regularization technique, you prefer the estimate here, which at least doesn't have that bias in it. On the other hand, what if you're not so concerned with inference? Maybe it's prediction that you're concerned with, in which case, these lasso models can be good, or especially some of these other procedures, more advanced procedures, they're really built for predictive modeling in a linear model context, in which case you probably want to go strictly with the model that you've already estimated right here. But again, I'm not trying to plant my flag about what's correct or incorrect, just trying to summarize some of the main issues here. I see another one just came in. Is there any automated control for correlations of predictors? Do we get variance inflation factors? The variance inflation factors. Yeah, so if you're interested in the VIFs, you're going to find them if you right-click inside a parameter estimates table and then go to columns. You're going to find VIFs living right here if you need to consult those. And that's in GenReg, and that's in your standard least squares. It's in all these parameter estimates tables. Great question. Thank you for asking that. I get that question very frequently. Okay. So I think that's clean in the Q&A. There's a lot of stuff in the chat, but I think everything in the chat maybe was... oh, okay. No, I see another one. Can you please explain how do you approach the optimization of lambda? There's no rule, lower, larger, better. Is that a fine line between number of variables and overfitting? Okay, so that's a good question that I just I talked about briefly here, but that is, how do we select the best lambda here? And the answer is that JMP is going to do that for you based on the validation method that you choose. So I chose the AIC. Lower values mean a better fit. If you're not familiar with AIC or BIC, they're based on the likelihoods. That is essentially the probability that the model assigns to the observed data, where we want a model that assigns the highest probability to the data. But an overfit model will assign really high probability to the data. So you want to basically penalize models for getting too complicated, that having too many effects. The AIC and the BIC do that. So it's like based on the likelihood, but then you penalize model complexity. And so with that as your measure, your validation method or your criterion or your measure of what constitutes a quote unquote good model, JMP then does that grid search. So it fits a bunch of models with a bunch of different lambda values and then returns the best one. And so that's what this graph is telling us right here. AIC, lowest AIC value was observed right here, which corresponds to a lambda of 15.4. And then we can see that that was, again, this model with the 3 zeroed out parameters right here. So that was the long answer. The short answer is you don't have to approach the optimization of lambda. It's built into JMP to just do that for you. Though, as I pointed out briefly, under the advanced controls, you can at least have some control over how that's done, like how many different lambda values to try and what the grid scale looks like. And some other stuff as well that I won't get into unless we need to.